All right, today we are diving into one of the absolutely strangest, most mind-bending ideas in all of physics. We're talking about a force that seems to appear out of nowhere, acting in a place that's supposed to be completely, totally empty. So let's just start with a little thought experiment. I want you to picture two mirrors. They are perfectly smooth and they have no electric charge at all. Now you take these mirrors and you put them inside a perfect vacuum. I mean, nothing is in there. No air, no particles, zip. And then you bring them incredibly close together. What do you think happens? I mean, logic would tell you nothing, right? There's no charge, no gravity to speak of, no air pressure. They should just float there. But they don't. The answer is they attract. Yeah, you heard me right. With seemingly nothing acting on them, these two mirrors start pulling themselves toward each other. And this isn't some trick question. It's a real, measurable phenomenon. So what in the world is this force? Where does it come from if it's literally born from nothing? Well, it has a name, and digging into it is going to completely change how you think about empty space. This is called the Casimir Effect. It's an attractive force that pops up between two uncharged parallel plates when they're in a vacuum. It was first predicted way back in 1948 by a Dutch physicist named Hendrik Casimir. And honestly, he just kind of stumbled upon it while he was studying something completely different about how molecules interact. Now, you have to understand, the scale of this force is fantastically small. If you have two plates, each one a square centimeter, and you separate them by just 1 micrometer, the force is about zero point 0.1 micronewtons. That is so incredibly faint, which, as you can imagine, is exactly why it was so insanely difficult to actually measure for decades. So how is this even possible? Where could this force be coming from? Well, to get that, we need to take a little trip into the true nature of empty space, into the buzzing, chaotic, and frankly bizarre world of the quantum vacuum. Okay, so the first and most important idea you have to wrap your head around is this. The vacuum isn't actually empty. Everything our intuition tells us about nothingness is just plain wrong when you get down to the quantum level. So what is it then? Well, in reality, what we call empty space is this seething, energetic sea of something physicists call quantum vacuum fluctuations. It's a total chaos of temporary or virtual particles and energy waves that are constantly popping into existence from absolutely nothing and then annihilating each other back into nothing an instant later. Space isn't empty. It's literally buzzing with energy. So how does a bunch of buzzing nothingness create a real force? Well, think of the vacuum like a huge ocean, with these virtual waves of all possible sizes surging through space. But when you put those two plates really close together, you basically create a narrow channel, and inside that little channel, only the waves that fit just right are allowed to exist. All the bigger waves get excluded. What that means is there are fewer possible waves, and therefore less energy, between the plates than there are in the wide open space outside. This imbalance creates a real-world pressure from the outside, pushing the plates together. It's literally a force created by excluding some of that nothing. Predicting something like this is one thing, but how on earth do you go about measuring an invisible force that's created by the vacuum itself? This is where the story gets really cool. It becomes a story about incredible human ingenuity. And let me tell you, the challenges were just immense. The force is ridiculously weak. The surfaces of the mirrors had to be almost perfectly smooth. Any tiny bit of stray static electricity would completely overwhelm the effect. And you had to measure the gap between them with nanometer precision. It was an absolute experimental nightmare. But, physicists are a persistent bunch. The first real shot at it was in 1958 by a guy named Sparnay. He did find an attractive force, but his error margin was a whopping 100%. So he couldn't rule it out, but he didn't prove it either. Then, almost 40 years go by. In 1997, Stephen Lamoro uses this incredibly delicate torsion pendulum and gets the error down to 5%. Huge step. But then, just a year later, Umar Mohidin and his team came along with an atomic force microscope and just nailed it, confirming Casimir's wild prediction with an error of only 1 to 2%. And here's the stunning result. Look at this graph. The little squares are the actual measured data from the experiment. The solid line is what the theory predicts the force should be. The match? It's flawless. It is a beautiful, undeniable confirmation of one of the wildest ideas to ever come out of quantum mechanics. But hold on, the story doesn't stop with two simple mirrors. Physicists started digging, and they found that this isn't just one weird, isolated effect. It's a whole family of forces born from fluctuations, and it shows that this is still a super active and exciting area of research. So it turns out there's more than one kind of Casimir force. The quantum effect we've been talking about, that's driven by vacuum fluctuations, but there's also a thermal version called the critical Casimir effect, which happens not in a vacuum, but in a fluid mixture that's right near a tipping point. This force is generated by thermal fluctuations, the jiggling of molecules. And here's the really amazing part. This version can be either attractive or repulsive. So how do you even measure that? Well, scientists use these awesome tools called optical tweezers, which are basically just super focused laser beams to hold a tiny little silica bead inside a liquid mixture. And by getting that liquid right to its critical temperature, they can actually measure the tiny push or pull on that bead caused by all the thermal chaos in the liquid around it. And this leads to something absolutely incredible. A quote from the research paper says it all. They found that the force can be easily turned from attractive to repulsive just by changing the chemical coating on the bead and the surface nearby. Think about that. We now have a switch, a way to control these strange forces at the nanoscale. And just when you thought it couldn't get any weirder, it does. There's another one called the dynamic Casimir effect. The theory says if you could somehow wiggle a mirror back and forth extremely fast, like at a good fraction of the speed of light, you would shake up those virtual photons in the vacuum so violently that they'd become real photons. You could literally create light from a dark, empty vacuum. It sounds like pure science fiction, but this has actually been seen in experiments that use superconducting circuits that act like these rapidly moving mirrors. So, a faint, bizarre force from the vacuum with even stranger variations. You might be wondering, why does any of this matter outside of a physics lab? Well, as it turns out, the implications are profound. They stretch all the way from the tiniest machines we can build to the very structure of the universe itself. At the tiny scale of nanotechnology, the Casimir effect is a huge deal. A lot of the time, it's actually a problem. It causes this thing called stiction, where microscopic machine parts literally get stuck together and stop working. But people are also trying to harness it, exploring ideas like using it to help pack hydrogen atoms into carbon nanotubes for fuel storage, or to build tiny little switches in microdevices. But here is the most mind-bending application of all. These incredibly precise experiments are now being used as tools to hunt for brand new laws of physics. Some theories, like string theory, predict that there are tiny, curled-up extra dimensions of space. If they exist, they should create new forces that only show up at these super short distances. So by measuring the Casimir force with extreme accuracy and looking for tiny little deviations from what our current theories predict, physicists are literally hunting for the first real evidence of those extra dimensions. A force from nothing is testing the very fabric of reality. And that kind of leaves us with this final, massive thought. The Casimir effect proves that the vacuum, the nothing that we see as empty and dead, is actually a dynamic, powerful, and fundamental part of our universe. It can push and it can pull on the world we see. And it just makes you wonder, if empty space holds this much power, what else is hiding in the vacuum?